All right, so today we're going to look at section 1.5. Now, there is a section 1.6, but section 1.6 is a review. I mean, there's no new material in section 1.6. And I believe the test for well, the test for chapter 1, I believe that's due on Friday. But I may, not may, I will extend that test date until Sunday at midnight. And so I think I'll just extend all of the tests Sunday at midnight just to give you some time instead of pushing on Friday. All right, so today what we're going to do is we'll take a look at interval notation. And we're also going to take a look at domain and range again. The last time we looked at domain and range, we looked at domain and range and how it related to a graph. Right, the domain was the stretch of the graph across the x-axis. I'm going to see if I can pull that up. And the range was the stretch of the graph across the y-axis. Because this is some of the stuff that did not get recorded the last time. Yes, right here. The domain is the stretch of the graph across the x-axis. The range is the stretch of the graph across the y-axis. We had taken a look at a couple of graphs. Can we kind of pull the domain and the range from those graphs? Today we're going to find the domain and the range if you're given a function. All right. But before we do that, we're going to take a look at interval notation. So I am actually going back to Blackboard. Okay, I'm going to go to our home page. I'm going to go into lecture notes. And I'm going to look at section 1.2. And we're going to take a look at this slide, okay? All right, and it deals with interval notation. So in interval notation, okay, interval notation is used if you are solving an inequality and the solution is more than one value. Okay, we express the solution set in the form of an interval. We have what's called set builder notation. So if you look in the second column, right, set builder notation, it has greater than, less than, greater than and equal to, less than, equal to, and there's also equal to and not equal to, which are inequalities. Then we have what's called interval notation. Now in this course, when we deal with intervals, and especially with domain and range, the answers will have to be expressed in interval notation. And if we look at the last column on the slide, we see a graph. Okay, now as far as this slide is concerned, everything is sort of abstract with just A's and B's and a bunch of graphs. What I'm going to do is put some numbers to the set builder notation. So what we're going to do is we're basically going to take set builder notation, we're going to graph it, and we're going to then express it as interval notation. Okay, and as you'll see, the rough sketch of a graph is basically the interval notation solution that we're going to use. All right, so I'm just going to make 3 columns. In the first column, we have set builder notation. In the next column, we have graph. And And in the third column, we have interval notation. Right. So if I go back for just a second. All right, now as we read this very first set builder notation, it says all real values x, and this vertical bar is read as such that x is greater than a. Now, when we write our set builder notation, we don't really write x in that such that. We pretty much just write either x is greater than a, x is less than a, so on and so forth. Okay. All right, so here are some examples. All right, so let's just say we have the set builder notation x is greater than 2. All right, and we want to express that in interval notation. So what I'm going to do is I'm going to just draw a quick sketch of a graph, right? I'm not going to draw out an elaborate graph. I'm mainly going to take my graph, I'm going to center it at 2. To the leftmost on my graph, I'm going to put negative infinity. Right, so keep in mind that negative infinity, those values keep going on forever and ever and ever. They get smaller and smaller and smaller. To the rightmost of my graph, I'm going to put positive infinity. Right, so positive infinity alludes to the numbers get bigger and bigger and bigger without end. Now, as far as XYZ homework is concerned, in order to display either negative infinity or positive infinity, you must use double O's. Okay, so OO in XYZ represents the infinity symbol. Okay. All right, so I've drawn out a quick sketch of a graph. So now we want x is greater than 2. Now, if we were using open circles and closed circles, right? So for open circles, we would use greater than and less than. For closed circles, we would use greater than equal to or less than equal to. But in interval notation, we don't use open circles and closed circles. We use parentheses and brackets, right? So if we were to graph this just using open circles and closed circles, I would use an open circle, right? Because we have x is greater than 2, so we would use an open circle. We want all numbers greater than 2, so that line would extend to the right, which is our graph. Okay, but for interval notation, we don't use open circles, we use parentheses. Right, so I'm going to change this open circle, I'm going to change that to a parenthesis, and that parenthesis should face the right. The line is going to extend to the right, and that would be the graph for x is greater than 2. So pretty much what I see on the graph, that is my interval notation. So I have the open interval from 2 to infinity. All right, so you can write x is greater than 2 as the open interval from 2 to infinity. All right, so let's look at the next one. X is greater than or equal to 2. All right, so keep in mind our goal is to rewrite these things in interval notation. Okay, so here again, I want to make a quick sketch of a graph. I'm going to center it at 2. negative infinity to the left, positive infinity to the right. So here we have x is greater than or equal to 2. Now, if I was using open and closed circles, I would use a closed circle because of the equal to bar. All right, so keep in mind that x is not greater than 2, but x can be equal to 2. So that equal to part of my inequality forces a closed circle. All right, so here again, we want all numbers greater than or equal to 2. So our line is going to extend to the right. And this would be our graph. But when we are using interval notation, we don't use open circles or closed circles. We use brackets, right? Either a left bracket or a right bracket. Right? Therefore, I'm going to change that open circle to a bracket. I'm going to make that bracket face the right. And that is the interval notation solution. Right? It's the half open interval from 2 to infinity. And I say half open because I have one parenthesis and I have one bracket, right? So that's a half open interval. All right, so now we're going to look at less than. All right, so I'm going to put in x is less than 2. So I am going to draw a quick sketch of a graph centered at 2. Negative infinity to the left, positive infinity to the right. I want all numbers that are less than 2. So at 2, I'm going to draw a parenthesis, and that parenthesis should face the left. The line should extend to the left, and that is our graph. Okay, so now I'm just going to translate that graph into interval notation. Right, so this would be written as the open interval from negative infinity to 2. Okay, so just notice a couple things about our intervals. Notice that for the interval, the smallest value is always on the left. The biggest value is always on the right. All right, so next we're going to look at x is less than or equal to 2. So I'm going to draw a number line centered at 2. Negative infinity to the left, positive infinity to the right. Since we have an equal to bar, we're going to use a bracket. That bracket should face the left because we want all numbers less than or equal to 2. So that bracket faces the left. The line extends to the left, and we have our graph. So the interval notation here is the half open interval from negative infinity to positive 2. And notice that whenever you use infinity, you must enclose infinity with a parenthesis always. Okay, a bracket implies that it stops, but keep in mind that infinity never stops. Okay. Next, we're going to look at what are called, bless you, compound intervals. All right, so a compound interval looks like this. 3 negative 3 is less than x is less than 5. All right. Okay, so how would we write something like this in interval notation? So now this is a compound inequality, and it's actually telling us two things at one time. All right. If I look at the first part, it tells us that -3 is less than x. I can actually rewrite that. The set builder notations we looked at previously, notice that our variable was on the left, right? If your variable is on the left, you can use the inequality to determine which way your bracket or your parentheses should face. You can also use it to tell which direction your line should go. All right, so if I look back at the first one, x is greater than 2. So notice that that greater than points to the right. So notice my parentheses to the right, my line is to the right. If I look at x is less than 2, all right, notice that the inequality points toward the left. All right, so my parenthesis faces the left and my line goes to the left. But when I look at -3 is less than x, that sort of breaks the rule from what we were doing. So I can actually rewrite -3 is less than x as x is greater than -3. All right, so notice when you reverse that inequality around, so notice that if I look at -3 is less than x, so notice that my inequality is opening up toward x. When I flip that inequality over, it should still open up toward x. So -3 is less than x is the exact same thing as x is greater than -3. And at the same time, x is less than 5. So we're going to make a rough sketch of this graph. So I'm going to draw a number line centered at -3 and 5. Right. I'm still going to put negative infinity to the left and positive infinity to the right. All right. So we're going to graph the first half of that inequality. -3 is less than x is the same thing as x is greater than -3. Right? So if I look at the bottom, my parenthesis, right, since I don't have an equal to, but I'm going to use a parenthesis at -3 that should face the right. And then my line is going to extend to the right. And x is less than 5, so for that inequality, my variable x is on the left-hand side. So I know that my parentheses should face the left and my line should extend to the left. Right, so that is our interval. Right, so I'm going to write that in interval notation as parentheses -3 to 5 in parentheses. Right, so I'm going to take a lot of this stuff away. So now I'm just going to change the signs up a little bit. So -3 is less than or equal to x is less than or equal to 5. Right, so if I were to graph that, I'm going to center that -3 and 5, negative infinity to the left, positive infinity to the right. I'm going to rewrite the first part of that once again. -3 is less than or equal to x is the same thing as x is greater than or equal to -3. So if we graph the first part of this compound inequality at -3, we should have a bracket that faces the right. the line is going to extend to the right, and x is less than or equal to 5. So at 5, I'm going to have a bracket that faces the left, and my line extends to the left. So our interval notation is written as the closed interval from -3 to 5. All right. And then there's two other scenarios. I just want to make sure I run through all of them. All right, so let's grab this one. -3 is less than x is less than or equal to 5. And -3 is less than or equal to x is less than 5. All right, so for these latter two, they are just variations with the inequalities. All right, so for -3 is less than x is less than or equal to 5, I believe the graph is going to look like this. All right, and that is considered to be a half open interval. So just notice at -3, since we don't have the equal to bar, I'm using a parenthesis. However, for 5, we have the equal to bar, so that forces a bracket. And then for the very last one, okay, I believe it should look something like this. Okay, where we have a bracket at -3 and a parenthesis at 5. All right, so any questions about interval notation? Okay, so once you get your answer in set builder notation, if you're unsure about interval notation, just draw a quick sketch of a graph, and that sketch should actually be your interval notation solution. All right, so now we are going back to domain and range again. But this time we're going to look at the domain in the range of a function. All right, so first I want to start off with the classification of functions. Okay, we're going to do a few of these things. All right, so the first thing I want to look at is a linear function. And a linear function takes on this basic form y equal to x. Okay, so you notice we talked about linear slope-intercept form, which is y is equal to mx plus b. Notice you don't see an m. Well, m is understood to be 1. And then you don't see a b. B is understood to be 0. Right? This is just the standard form of a linear equation. When you graph a linear equation in this form, both a y and an x variable, you should get a graph that looks like that, right? So if you are talking about any linear function, right? So what actually makes this a linear function is that if I look at my x and my y variable, notice that they have understood powers of 1. All right, so mainly we just concentrate on the x variable because the y variable for the functions we're working with in this class always have a 1. Since my x variable is no higher than 1, then this is classified as a linear equation. For all linear equations, the domain is all real numbers, negative infinity to positive infinity. So if you're ever asked the domain of a linear function or a linear equation, it's always all real numbers, right? Negative infinity to positive infinity. Also, if you're asked for the range, it's the same thing, negative infinity to positive infinity. Okay, so if we go up on powers, the next thing is going to be a quadratic function. And the basic form of a quadratic function is y is equal to x squared. When you graph a quadratic function, you get what's called a parabola, which is a U-shaped graph. A parabola or U-shaped graph. So notice what makes this a quadratic function is that my exponent, the largest power, is a square. So that makes this a quadratic function. The domain of any quadratic function is all real numbers, right? Because both of these graphs will stretch the entire x-axis. Okay, now the range is not all real numbers. The range is going to be a little bit different, all right? So that depends upon the equation that you're given. And we're going to look at one more, a cubic function. Right, and a cubic function is in the basic form y is equal to x cubed. And if you graph a cubic function, you should get what's called an S-shaped graph. The domain of any cubic equation is all real numbers. The range of any cubic equation is all real numbers. So those are just facts as we go further. So for example, and I thought I was logged in. All right, so for this very first problem, it says for the following exercise, find the domain. So what type of equation is this? Let me just jot this down. So this is similar to number 1 in section 1.5. All right, so if I write that down, find the domain. So that was 1.5, number 1. F of x is equal to negative 2x, x plus 2, x minus 2. If you look at your x variable, right, you have 2x, you have x plus 2, and you got x minus 2. We have 3 x's. What is the largest power on x? Should be 1, right? So if I look at negative 2x, that x is understood to be raised to the first power. If I look at x plus 2, that x is understood to be raised to the first power. And if I look at x minus 2, that's understood to be raised to the first power. Since all of my x variable are raised to no higher than the first power, this is considered to be a linear function. So from what we just talked about, the domain of any linear function should be what? All real numbers. Negative infinity to, with a parenthesis, negative infinity to positive infinity. All right, so for number 1, and this is how you put in those infinity symbols. I'm going to put in a parenthesis, negative infinity, so I have to hit 00, comma, positive infinity, and that's our domain. Okay. I'm going to skip number 2 for right now, and let's look at number 3. That's 8 over x minus 9. And we're asked to find the domain. 1.5, number 3. F of x. Find the domain. F of x equals to 8 over x minus 9. All right, so when we talk about a function, all right, and we touched on this the last time, we have x and y, right? X is the domain, y is the range. X, which is the domain, that's your input. Right? That's the number you stick into the function. The y, which is the range, that is the output. Okay. Now, the reason why I talk about input and output is because when we deal with functions, all right, we want to look at the input and output aspect of things. Okay, so this is how this domain and range stuff works as far as a function. You cannot consider a number a domain value if you stick that number into the function and that function doesn't return an answer. Right? The only thing a domain is considered as a number you put into a function and it gives you output. That's a domain value. Since we are dealing with a fraction, there's certain things about fractions. 0 over any number. That could be 0 over a million. That could be 0 over negative a million. 0 over any number is 0. And I'm actually going to pull up this calculator to verify that if it wants to come up. All right, so in this calculator, I'm just going to turn it on. I can put 0 over 100. It's 100. 0 divided by 100 is 0. 0 divided by negative 100 is 0. But the other way around, if 0 is in your denominator, you have something undefined. You cannot divide by 0. So my calculator, let's say if I put in 100 divided by 0, $100 divided by 0, I'm going to get an error. Say can't divide by 0. All right, so now with that reason, if we take a look at this problem, right, 8 divided by x minus 9, is there some number that's going to make the denominator equal 0? If so, we cannot use that number or numbers as a domain value. So if you're asked to find, even though this is linear, right? Since it's a rational function, right? We have a numerator and denominator. We have to figure out what number make or numbers make the denominator equal to 0. Right? So I'm going to take the denominator. Since we have a rational function, we're going to set the denominator equal to 0 and solve. Right? So whenever you're asked to find the domain of a rational function, so keep in mind that rational is just another word for fraction. We take only the denominator, set it equal to 0, and solve. All right, so I'm going to take this denominator, which is x minus 9, set that equal to 0. So we would add 9 to both sides. So x is going to equal to 9. Right, so what does that mean? Well, that means that 9 is a match. We can use any number except for 9. Right, because if we use 9, we get 8 over 0, which is undefined. So when we stick 9 into that function, it doesn't give us an output value. Therefore, we cannot use 9 as a domain value. So what I want to do is I want to write out the interval notation, but I want to cut out 9. Right? So here's how I'm going to do that. So I'm going to write negative infinity to 9. And I'm going to use a parenthesis at 9 because I can't actually use 9. Or I can use the numbers from 9, but not including 9 to infinity. So this is the number line with the number 9 taken out. Okay. All right, so we noticed that it was a rational equation. We took the denominator, set it equal to 0, and we found that 9 was the number that makes the denominator equal to 0, right? So 9 is not the domain, right? That's not the answer. That's the number we need to stay away from. So we wrote out the interval as negative infinity to 9, union 9 to infinity. And I'm going to put that in as parenthesis negative 00, comma 9. You have to put in that U for union. Nine to infinity. All right, so any questions about number 3? That's right. Just take the denominator only, set it equal to 0, and solve it. Sometimes you may get 2 answers, all depend on your equation. All right, now we're going to look at number 2. But before we look at number 2, let me just write that down. F of x is equal to the square root of 2 minus 9x. Okay. All right, so before we actually look at number 2, I have to review this first before we take a look at number 2. We want to solve inequalities. All right, so this is just a review. It should be a review. And you'll see why this makes sense to what we're doing in a second. So let's just say we want to solve two x is greater than 10. Okay, just a simple. All right, so here again, we would treat this inequality just as an equal sign, right? We would use those 6 steps. The first step is to remove the fractions. The second step is to remove parentheses, which we don't have any of those. The third step would be to use combine like terms. We don't have any like terms on either side. The fourth step is to use the addition property of equality, which we're not going to use, but we will use the fifth step. We're going to divide both sides by 2, right? So if I divide both sides by 2, x is greater than 5. Right? For the second example, let's look at negative 2x is greater than 10. And this is where, I'm not going to say the problems come in, but this is where you can go along a lot of times if you don't keep this rule in mind. So the same thing, just like in the first one, we divided both sides by 2. Here we're going to divide both sides by negative 2. But this is a rule. When you multiply or divide an inequality by a negative number, anybody remember what you got to do? You have to reverse the sign. You must reverse the sign. Right, so what does that mean? So here we have negative 2x is greater than 10. We want to divide both sides by negative 2. So that means we have to take our inequality and we must flip it over. So the solution here is x is less than -5. Okay. So it doesn't matter if the number is negative or positive, the end or whatever. So, but what does matter, if you multiply or divide by a negative, you must reverse your sign. Okay. All right. And I want to talk about square roots. So y is equal to the square root of x. All right, so I'm going to pull up the calculator and I'm going to graph the square root. Okay, and the square root, it basically takes a general shape like this. So I'm going to turn on the calculator, clear out that home screen. I'm going to go to y equals, and I'm going to put in the square root. So I'm going to hit, well, I'm going to clear that equation out first. I'm going to hit second and x squared, which gives me the square root. I'm going to put in x, and I'm going to graph by using Zoom 6. Right. So notice what the graph looks like. All right. Can anybody tell me why the graph doesn't exist on the left-hand side? That's right, because we can't have negative numbers inside of a square root. For example, the square root of -2, well, I'm going to use 4. Right? If I were to go into the calculator and if I were to put in the square root of -4, let's just see what happens. The square root of -4 is not a real number. Now we're going to talk about imaginary numbers, but for now, the square root of, you cannot have the square root of a negative number, okay, because it's not a real number unless you make up one. It's called imaginary number. We'll talk about that a little bit later. All right. So now I want you to keep this in mind as we find the domain for, come on, as we find the domain for this example. I think this was number 2. Yeah, number 2. 1.5, number 2. We're asked to find the domain for f of x is equal to the square root of 2 minus 9x. All right. So first off, since we're dealing with a square root, there's going to be certain numbers that we can't use because depending upon what number we substitute in for x, that could give us something negative, right? So whenever you're asked to find the domain of a square root, to find the domain of a square root, you must take the square root and set equal to, or set greater than or equal to 0. So you have to treat rational functions a little bit different. Right? For that fractional function, you have to take the denominator, set it to equal 0. For a square root, you must take the square root and set the square root to greater than or equal to 0. Right? The reason why we have to set it to greater than or equal to 0 and not just equal to 0 is because you can have the square root of any positive number. Right? I mean, it may be perfect, like the square root of 4 is perfectly 2, or it may not be a perfect square, like the square root of 2. Where's my calculator? All right, so like the square root of 4 should be 2. The square root of 2 is an irrational number. All right, but it returns a value nonetheless. All right, so for this problem, I want to take my square root, which is 2 minus 9x. I want to set that to greater than or equal to 0. Right? The reason why we're going to include 0 is because if you were to take the square root of 0, you get an answer in return, which is 0. All right. So we can use 0 as a domain value because it returns a result. All right, so how do we solve this? So we want to solve it for x, right? But as it stands, the x is trapped inside of the square root. What could we do to both sides to cancel out the square root? Square both sides, right? Because the square root and the square will undo each other. So I'm going to just put this step in. So we're going to take the left-hand side, which is 2 minus 9x. We're going to square that. And from our properties of equality, whatever you do to one side, you must do the exact same thing to the other side. So I'm going to bring down my greater than or equal to inequality, and I'm going to square the right-hand side, which is 0. So on the left-hand side, the square root and the square cancel, and we're left with 2 minus 9x, which is greater than 0, right? Because 0 squared is 0. Right, and now we need to solve it for x. So what should we do from this point? Right, we're going to subtract 2 from both sides. We're going to transpose 2. So we have negative 9x is greater than or equal to negative 2. And our last step is to do what? Okay, the opposite of multiplying by negative 9 is to divide by negative 9. And since we're dividing this inequality by a negative number, we must do what to the inequality? We have to reverse it. Right? So I'm going to reverse that inequality. And I'm going to write this step in. I'll do that. Okay, we divide both sides by negative 9. So notice I reverse my inequality. The negative 9's cancel, so we have x is less than or equal to a negative divided by a negative gives us a positive 2/9. Now we want to put this in interval notation. So I'm going to make out a graph that's just centered at 2/9. We want all numbers x such that x is less than or equal to 2/9. So since my variable is on the left-hand side of the inequality, my inequality is pointing toward the left, so I can draw my bracket, right? Because we have this equal to bar, I can draw a bracket that faces the left, and our line should extend to the left. So we can write this as an inequality of, right, a parenthesis, negative infinity, comma, 2/9 with a bracket. Right, so we have the half open interval from negative infinity to 2/9. Right, so I'm going to go back. So it's an open parenthesis, 0, 0 for infinity, comma, 2/9. Oh, negative infinity. Yeah. Did I put it on here? Oh, yeah, yeah, negative infinity. Come on. There we go. Negative infinity to. Did I put a period? Let me try that again. Oh, I should put a bracket. Yeah. Negative infinity to 2/9, and I think that's it. Okay. All right. Any questions about number 2? All right. Just kind of looking at the rest of these. For problem number 4, that's a fractional equation. So you basically just take that denominator, set it equal to 0. Right. Once you get that solution, however, you must take that number out of your domain. Okay, such as we did number 3. See. Okay, let's take a look at number 5. We're asked to write the domain and the range for problem number 5. And I can't actually write on this. That's about the only. Let me see if I can copy and paste this. No, it won't let me do it. Okay. All right, so nonetheless, let's take a look at the domain. I'm just going to blow this up. And remember that the domain is the stretch of your graph across the x-axis, right? All the x values that your graph has. So notice this graph starts from here, which is -6. And notice that there is an open circle at -6. Right? So at -6, I'm going to use a parenthesis. And it stretches across the x-axis until about 4, +4. So notice at 4, there is a closed circle. So I believe the domain here is -6 with the parenthesis to 4 with the bracket. All right, so if I can actually write on this, I would draw a horizontal line at the bottom. And if we look at the range, so keep in mind the range are all of the y values that your graph can take on. So if I look at this first open circle point, it seems like it stretches or starts at -1. So with -1, I'm going to use a parenthesis. And it stretches all the way up to +6 with the bracket. So my range is from -1, oh my goodness, -1 with the parenthesis, comma 6 with a bracket. So that's the domain and the range of a graph. All And I believe the rest of these problems, all right, are pretty much the same. All right, and if we take a look at section 1.6, the problems in 1.6, well, I guess we should talk about increasing and decreasing functions. Okay, so this is number 1, and it says determine whether the function is increasing or is decreasing. Well, I guess we'll tell you what, we're just going to graph these using a calculator. But I guess before that, based on what we know about a linear equation, we classified slopes, and if the number part of x is positive, can I delete this? Classification of slopes. Okay, so if you read a graph from left to right and that slope is positive, that means that that graph is increasing, right? Because it's always going up. If you read a graph from left to right, and these are for linear equations, as far as the slope is concerned, if you read a graph from left to right and the graph is decreasing or descending or going down, the number part of x is negative, and that is decreasing. All right, so guess using those facts, if we were to take a look at this problem, f of x is equal to 2x minus 5, do you think this graph is going to increase or decrease? Well, in order to determine, we're going to, since we know it's a linear equation, we're going to look at the number part of x. Since that number part of x is positive, then that graph should increase. So that's one way to do it if you're just going to use facts. Another way to do it is I could actually graph it in the calculator and take a look at what's going on. All right, so I'm just going to turn the calculator back on. I'm going to go on a y equals. I'm going to clear out that equation. I'm going to put in 2x plus 5. I'm going to graph. Right, and notice that that graph increases from left to right. Okay, what about number 2? H of x is equal to negative 1/3 x minus 2. Well, this is a linear equation. The coefficient of x is your slope. The coefficient of x is negative, so that graph should decrease. All right, I do not want you to miss these on the test. Okay. And then the next one says find the slope of the line that passes through 2 points. Is everybody okay with that? This is another one that says find the slope through 2 points. This says given the set of information, find a linear equation that satisfies the conditions. Is everybody okay with that? That's still like 2 points. This says determine whether the lines are parallel, perpendicular, or neither. Is everybody okay with that one? Yes, no, maybe, I don't care. I'm ready to go. All right. This one says find the x and y intercepts. Right. To find the x-intercept, you let y equal 0. To find the y-intercept, you let y equal to 0. Is everybody okay with that one? Find the equation for the line parallel to f of x is negative 4x plus 3 and passes through 4 comma negative 15. You will see that on the test. Is everybody okay with that one? Okay, this is the same type. Is everybody okay with the perpendicular stuff? Let me work this one out because on the lecture got all, it just went left the other day. There may be some people in the online land that. Okay, we got enough time. I'll just do this one. Let me just write this down. F of x is equal to negative 2x minus 1, and it passes through 4 comma negative 2. And it's perpendicular. Find an equation perpendicular to f of x is equal to negative 2x minus 1 and passes through 4 comma negative 2. All right. So the first thing we're going to do is find the slope. All right, so we're given that f of x is negative 2x minus 1. So our slope is negative 2. But we're not going to use a slope of negative 2 because if we use a slope of negative 2, then we're going to find a parallel equation, right? Where we specifically want a perpendicular equation, right? So from what we talked about the last class, two lines are perpendicular if they intersect and form a perfect 90-degree or 90-degree angles, or if one slope is the negative reciprocal of the other slope. Okay. So here we're going to find the negative reciprocal. Right, so we're going to take negative 2. First, we're going to find the reciprocal. Right, so negative 2 can be written as negative 2 over 1, right? I'm going to reciprocate that, and I have negative 1/2. Right, so when you take the reciprocal of any number, the sign doesn't change. Right, you just flip-flop the numerator and denominator. Now that we've taken the reciprocal, the next thing we want to do is multiply by negative 1. Right. So I have the negative 1/2, which was my reciprocal. I'm multiplying that by a negative. So we have positive 1/2 as our slope. So the next thing we're going to do is substitute or find the equation using point slope form. M is equal to 1/2, and the point on the line is 4 comma negative 2. So above 4 comma negative 2, I'm going to rewrite x of 1 comma y sub 1. I'm going to rewrite point slope form, which is y minus y1 is equal to m times x minus x of 1. So remember, you never know x and y, but you should know m, x of 1, and y sub 1. So we should be careful on the substitution. So we have y minus, right, because there's a minus in the formula. Y sub 1 is a negative 2, so you must substitute y sub 1 for negative 2. That's equal to 1/2, which is the slope, times x minus 4. On the left-hand side, I'm going to write that double negative as a positive. On the right-hand side, I'm going to distribute 1/2. So 1/2 times x is 1/2 x. A positive times a negative is a negative. And 1/2 of 4 is 2. And now we're going to solve it for y. So we're going to subtract 2 from both sides. So we should have y is equal to 1/2 x minus 4 as a solution. Right, so any questions about that one? Let's see. Okay, this says find the slope. The best thing to do on this problem is I would find points that they evenly intersect at a value. So like for this one, I don't know if you all can see that. I can see like right here at this point, 0, 3. I could use that as, well, you could actually do it two ways. You can count the slope by hand, or you could use the formula. So I would use this point 0, 3. And I would also use this point, right, -2, 2. So it looks like since the graph is going up, the slope should be positive. So it looks like my run is 1, 2. My rise is 1, 2, 3, 4, 5. So it looks like the slope should be 5/2. 1, 2, 3, 4, 5. Or you could use a formula. Okay? But notice the points that I chose, they were at intersections, right? I didn't choose this one because I can't exactly determine the value of that point. All right, so keep that in mind. Okay, what is the equation for this line? Remember we had two types. If it's horizontal, we talked about the roof over there, that's y equals to something. And if you have a vertical line, it's x equal to something. So here notice that the y value always has the equal to. Right? So it doesn't matter what x is equal to, but for all these ordered pair points, the y coordinate is 2, so y would have to equal 2. All right. All right. So as you kind of noticing, these things are just, the only thing new in this last section was just the increasing and the decreasing part. All right. So at this time,